Okay. Number 2. So state and prove Cayley's theorem. So this time I have a student's submission, because I think it's pretty good, and it's pretty much what I would end up writing down anyway. So it goes up like this, right? Cayley's theorem is let G be a group, and then that means G is isomorphic with a subgroup of SG. Or in other words, every group is isomorphic to some group of permutations. So remember that SG is the set of all permutations of G with the operation of function composition. So everything in there is a permutation on G. In other words, it's a bijection from the function from G to G, which is totally bijective and one-to-one and everything. So it's a nice permutation. And SG is all of them together with the operation of composition. And it turns out that that's isomorphic, or that some subgroup of that is isomorphic to G. So let's see what subgroup that is. So this person wisely defines a function from G to SG called phi, and what it does is it takes in an element of G. What the heck? Takes in an element of G and turns it into this thing, lambda sub x. And what is that? Well, lambda sub x is itself a function because it's an element of SG, and things in SG are functions on G. So this lambda x should take in an element of G and spit out something else, spit out some other element of G. And so, according to what they're saying here, lambda x is the function which multiplies stuff on the left by x, calling it the left representation. That's, yeah. Whoops, this is not all the way out here. Okay, so, yeah, so we must verify that phi is a group homomorphism and that it's also one-to-one. Yeah, because we need to make sure that it's an isomorphism, so we need to prove all those things. So, first of all, the image of it is a subgroup. Well, if it's a homomorphism, then yeah, that's true. So anyway, so we gotta prove those things. So first of all, phi is one-to-one. So how do you prove that? Well, you start with any two elements, A and B, and starting with this. Well, then you got to end up with this. And that's exactly what they did, right? So they said, well, if phi of A and phi of B are equal, then that means lambda A and lambda B are equal. And that means if they're equal as functions, then they should be equal whenever you plug anything in. So for example, let's try plugging in E. And what are those functions? Well, they're just the things that multiply on the left like that. And so boom, turns out A and B are equal. So phi is one-to-one. And then pretty much the same idea for homomorphism. It's true that it's a homomorphism. It's simply that you know, you look at these two expressions and make sure that they come out to be the same. And in this case, for phi, those two expressions are really these two expressions. So you got to show that those are the same. And sure enough, they are, because look, if this takes in any element of G, that's the same as you know, these guys taking in any element of G separately like that. You know, I wish that would stop happening. There you go. So yeah, so it turns out that it's one-to-one, and it's also a homomorphism. And you don't have to prove that it's onto, because it's kind of automatically onto whatever subgroup it's landing on. So you don't have to worry about onto. But now that you have its homomorphism, and it's one-to-one, and it's onto, so it's an isomorphism. So there you go. This is a perfect 10 solution by a student for number 2.